Yeah, hello all together. We are now starting a new chapter in our lectures, namely on spatial motions and similarities. We will use, of course, the techniques which we discussed the last lectures, especially the rotations, and we will have a look at spatial motions and similarities in several ways, and we will start with a general outline in this lecture. So we, of course, now have 3D coordinates, not 2D coordinates. We have 3D coordinates in the same manner as we did for the rotations. But as in the planar case, we also introduce homogeneous coordinates in 3D. You see the vector here is slanted for the non-homogeneous coordinates, and here upright for the homogeneous coordinates. So we have the u, v, w, t for components for this vector. We will generally call motions m, and similarities not s because it conflicts with the skew matrix. I use the letter A for Ähnlichkeiten in German. So because we don't have affinities, there is no difficulty in exchanging these two notions. So let's start with the spatial similarities. A spatial similarity is a scaling of a vector, a rotation, and afterwards a translation. And this gives the new point x prime. This is written down in non-homogeneous coordinates. So this is quite simple, and it would be the same equation in 2D. So now we have a concatenation of scalings, rotations, and translations, and that's the reason why we also here use homogeneous coordinates. So for a 3D point x, calligraphic, with non-homogeneous coordinates x, y, z, we have the homogeneous coordinates. This is just the 3 coordinates x, y, z with 1 added to it, and multiplied with some arbitrary factor t, which should not be 0. Then we get a homogeneous vector u, v, w, t. In our context, we will always assume t is 1, so things are simplified in the context of this lecture. And of course, if we have given a homogeneous vector u, v, w, t, we easily can derive the non-homogeneous coordinates by dividing the u, v, w by t. So this is exactly the same as in 2D, except that we have a w and a z here. Now, let's start with a translation. A translation is nothing else than multiplying this homogeneous vector with this matrix. You see here no scaling, no rotation, only the translation. So we, in the first instance, we have tx plus u, ty plus v, tx dz plus v, w. This leads us to the new vector u prime, v prime, etc. This is exactly the same form as in the 2D case. So the only difference here, if we put that together, we have this in compact form. So instead of a unit matrix of size 2, we have here unit matrix of size 3. Here rotation matrix 3 by 3. Here a unit matrix 3 by 3. And so you see these are exactly the same equations as before, except that they are have a 3 by 3 upper left block. Observe that this rotation matrix is a homogeneous matrix. So if we multiply this whole matrix by some factor, this is no rotation matrix, proper rotation matrix, because it has not determinant 1 anymore, but some other factor. But the R should be here, should be a proper rotation matrix. Okay, now if we now describe a similarity, we write this in this form. So we have similarity depending on rotation, translation, and scale. And we have here the mapping from x to x prime. And this is given by this relation. And you see that we have this now as a linear transformation of the homogeneous vector x to the homogeneous vector x prime. This is a 4 vector, this is a 4 vector, so we have here a 4 by 4 matrix A. This matrix can be understood as first performing a scaling, then a rotation. This gives us lambda times r, and then a translation, which gives us this expression. And of course, we could exchange the scaling and the rotation. This would make no difference. If we write down the inverse, we find out that the inverse transformation, depending on rotation, translation, and scaling, is nothing else than the inverse of this matrix here. So the R is transposed, the scale is inverted, and now we have an expression here which modifies the translation vector. Okay, that means we have a similar situation as in 2D. All similarities in 3D build a continuous group. It's a group property, so a concatenation of a similarity with another similarity gives a similarity. We have a zero element, that means the unit matrix, and we have an inverse element. The similarity has 7 degrees of freedom. That means the number of parameters which we need at least is 7. 3 rotations, 3 translations, and 1 scale. And of course, if we just take this expression here, we are free to represent the rotation. So we can do it with any of the representations which we discussed the last lectures. So if we choose another representation, not with 3 parameters, but with more, then of course those are not independent anymore, and we have to take this into account when we do the estimation. Now we come to spatial motions. This is very simple. We just omit the scale factor. So a motion, depending on a rotation, a 3D rotation, a 3D translation, is nothing else than rotating the vector and adding the translation. And if you write this in homogeneous coordinates, we get this expression, again a 4x4 matrix with the rotation part in the upper left and the translation part in the upper right. Of course, they also build a continuous group. This is the special 3D Euclidean group, which is sometimes abbreviated with SE and then the dimension 3. It has 6 degrees of freedom, namely 3 rotations and 3 translations. So up to now, this is quite simple. And now I want to mention one interesting point, that motions in 3D can interpret it as screw motions. What is a screw motion? You define a line, you rotate the object around this line and shift it along the line. So if we have here the line and the object is here, we move it like this. And the interesting thing is that any motion in 3D can be represented this way. So let's have a look at the 2D case. We have here in the plane, first imagine this is a plane. We have here a quadrangle and here a quadrangle with points A and B, which are mapped to A prime and B prime by a planar rotation. So we have here the rotation center. A is rotated to A prime, B is rotated to B prime. Now, let's assume we have given this red and this green figure. We easily can derive geometrically this rotation point by connecting A and A prime and taking the mid perpendicular, and do the same thing for B and B prime and take the mid perpendicular, intersect those, and we get the rotation point. This can be done always. So let's assume we move this green figure around. We'll see how the circles move, how the rotation point moves. Now we rotate the second object. That means we diminish the rotation, and of course then the point of rotation goes further away. And if we have a pure translation, like here, we can find out that this, of course, this rotation has straight lines in all directions. And we can continue with the rotation and get a rotation like this. So A is rotated to here, B to here, and the rotation center is here. Now let's assume we move the point A to the point A prime, so that they overlap. Then of course the center of rotation is the point A. So this shows that in 2D we always can describe a 2D motion as a rotation around a point. Now go one step further. Let's assume the red object is closer to us before the screen, and the green object is behind the screen. And assume that we look along the rotation axis. So we look at this situation in terms of there is a rotation axis. We know that every rotation in 2D has a rotation axis, so we take this. Now, if we imagine what happens here, we can imagine that the red object is in front of the, which is in front of the screen, is rotated and translated around and along this line L, which is perpendicular to the screen. So this is, so to say, the visualization of such a screw motion, which we can find for every arbitrary motion. So we have seen that every motion can be described as a screw motion. So we take the direction r of the rotation axis. The direction has two parameters in 3D. Then we can define a plane perpendicular to this axis of rotation and perform a planar motion in that plane. That's a rotation around some arbitrary point. This has three parameters, the point and the angle of rotation. And then we can translate the object in the direction of the rotation axis. So we have two parameters for the direction, three for the rotation and around an arbitrary point, and one for the translation along this direction. Now, if we want to formalize this, we start with a screw motion with respect to the z-axis. So let's assume we have the z-axis going upwards. We have a rotation around the z-axis. This is this part, cosine theta, sine and sine theta, like we know it from the rotation. And we have a translation along the z-axis by d. So this screw motion depends on two parameters. So if we have a screw motion along the z-axis, we have two parameters. Now let's assume we have an arbitrary line in 3D space. We can shift the line such that it passes through the origin, which is two parameters, because we can intersect the line with the xy axis. And then we can rotate the axis into the z-axis, which is again two parameters, because we have the description of the rotation direction, let's say with geographic coordinates, with lambda and phi. So we have another two parameters. Then we perform the screw motion, which is two parameters, and then we undo the rotation and the translation of this line of rotation. So again, we have two parameters for the rotation, two for the translation of the line, and we have two parameters here in this screw motion along the z-axis, again 6 parameters. And we always can represent a arbitrary motion in such a way. Now let's have a look at small motions and similarities. Why do we need them? Again, we need them for variance propagation or for estimation. So let's start with the parameterization. We have parameters, rotation, translation, and scale. And we have a mapping, a similarity from x to x prime with these parameters, or in this way. So this we know, and we can do the same thing, of course, for the rotation. We have a rotation parameter, r and t, collected in this s, which sometimes is called screw, because we have a screw motion. and the mapping, of course, is of this kind. So this is up to now what we know. Now let's assume we have a small similarity. What happens? So we have small changes around the approximate similarity, which is a unit matrix. Unit matrix would represent a rotation which is 0, a motion which is 0, and the scale factor is 1. So we have these approximate values. And if we now assume we have small or differential parameters, dp, we perform the dilation with 1 plus d lambda, the rotation with dr, and the translation with dt, and obtain a small similarity depending on the parameter dp. This is very useful if we want to describe the affinity as a function of these 7 parameters, if we want to do it rigorously. Now, if we now linearize at the unit matrix, we have up to first order terms. We have the nonlinear description of the similarity is the approximate similarity, which is the unit matrix, plus some change depending on these parameters. Now, how does this matrix dA0 look like? So it's a differential change of the similarity at 0 change, depending on these parameters. Now we remember that we had the same situation for the rotation. So if we change a 0 rotation differentially, we have found out that the rotation matrix changes in first order with the skew-symmetric matrix of the small rotation vector. So let's apply this and put it into our equation. So the small similarity, depending on these 7 parameters, is this small translation, and we have here the small rotation already linearized, and here 1 plus d lambda, which is the original. Now we take the product of these two and omit terms of second order, so the d lambda and the dr term product cancel, or we don't use them, and we come up with unit matrix plus d lambda times unit matrix plus the skew-symmetric matrix of the rotation vector. And here, of course, we have the dt. So now we observe that we have here the unit matrix and here the 1, so we can easily find out what the dA looks like here just by subtracting the unit matrix I index 4. So the change is now the skew-symmetric matrix. This is this part. Then we have the dt, and we have the scale part, which is this part. So we can write this in these components, or we can put that together in a matrix, or we can write this matrix out and look at the parameters. So you see the changes of the lambda on the diagonal, you see the translations on the upper right, and you see the skew-symmetric part of the rotation vector here with minus, plus, minus, dr 1, 2, 3. So this would be a small change of a similarity close to a unit matrix. That means to a 0 change of the similarity. So the same we would, of course, get for rotations. Then just the lambda is not in the equation, so we have this additive composition, or we have here the differential change of a homogeneous matrix, and the last element again is 0. We have here the translation, and here we have the skew-symmetric part of the rotation vector. Okay, this is the linearization at a 0 similarity. 0 similarity means you have 0 rotation, 0 translation, and 0 change of the scale. Now let's assume we have an arbitrary point. So we have an arbitrary matrix A, and I don't care how this matrix actually is represented with parameters. So we don't put the parameters here. Then we multiply this matrix with a similarity which depends on small parameters or differential parameters, dp. and obtain our similarity. Now, the dp is, of course, the differentials of the rotation vector, the translation vector, and the scale parameter. And if we multiply this out, of course, we get that what we just derived. Okay, now let's make an example. Let's assume we want to derive the uncertainty of a point which is transformed by a similarity transformation. So the uncertain point is described by its mean vector, which is a 3 vector, and a covariance matrix 3 by 3. Now, what is the representation for homogeneous coordinates? So we have here the homogeneous coordinate, which is uncertain, underlined. It's also normally distributed with some mean vector. Now, what stands in this mean vector? We have the mean of x, the mean of y, and the mean of z, and 1. So this is simple. And how does it look with the covariance matrix? Now, the covariance matrix of the first 3 elements, of course, is this 3 by 3 covariance matrix of the non-homogeneous vector. And because the last element here, the mu 4, is 1, its standard deviation is 0, and consequently the correlations between this 4th element and the first 3 elements also is 0. That means the covariance here stands the covariance of the vector x, y, z and the scalar 1, which is 0. Let's assume we have this given, and in addition we have an uncertain similarity with some mean value for the similarity. We don't care where this comes from. And we say the uncertain similarity is the product of this mean multiplied with a similarity depending on a small disturbing vector delta p, which is stochastic. And the covariance matrix of this vector is described by some distribution, let's say normal distribution, with mean value 0, that's a 7 vector 0, and a 7 by 7 matrix for the 7 parameters of the similarity. Let's assume these two things are given, and we would like to know what is the uncertainty of the transformed vector x prime. So x is uncertain, a is uncertain, consequently x prime is also uncertain, so we have underlines in all 3 elements. So how to approach this? We of course start with the total differential of the similarity transformation, which is nothing else than dx prime is the differential of a multiplied with x plus a multiplied with the differential of x. So this in the first instance is simple. The problem is that the dA depends on 7 parameters. So it's a 4 by 4 matrix which depends on 7 parameters. And we don't know the covariance matrix of the 4 by 4 elements, but only the covariance matrix of the 7 elements. So we need to know, use the relation between the A and the A0 and the A depending on these 7 parameters. So if we take the differential of this equation, we get dA is dA approximated as 0 of dp multiplied with a evaluated at the approximate values. So we use this expression here, plug it in here, so we get dx prime is dA, which is dA0 of dp multiplied with a multiplied with x plus a dx. Now we are not finished because this might be awkward to write this down. We can do this, but it's not on the right hand side, which we would like to have for variance propagation. So we would like to have a description of this relation of dx prime as a function of dp and dx with the Jacobians of x prime with respect to the changes of the parameters and the Jacobian of the coordinates x prime with respect to the given coordinates. So we have to find these two Jacobians. This one is easy because we see directly this is A. So this is a simple part. So the Jacobian of the transformed points with respect to the given point is nothing else than the matrix A evaluated at the approximate position. Now, if we write down the dx prime as a function of the dp's, we start with this expression, which we know. Now, what is this part? This is nothing else than d lambda multiplied with the unit matrix, the skew-symmetric matrix of the small change of the rotation, and here on the upper right, the change of the translation, multiplied with ax. What is ax? Yeah, at the approximate values, it's x prime. So we could say this is x prime. So we get exactly the same expression multiplied with x prime. One, of course, we have to take into account that the x prime depends on the approximate values of the transformation. Now, this is an expression where the right-hand sides are x prime and not the unknown parameters. So we rewrite this in the following form. So let's have a look. So S multiplied with dr, S of dr multiplied with x prime is the cross product of dr and x prime. And that's the cross product of minus x prime and dr. So there we are. The second is the dt. The dt is nothing else than unit matrix multiplied with dt. And the scale parameter is lambda, d lambda multiplied with x prime. So we get x prime multiplied with d lambda. Now we have obviously found a representation where the dx prime, the differential of our transformed point, dx prime, depends on the differential parameters. And that means this is the Jacobian which we need. So the Jacobian of our transformed point with respect to the parameters is nothing else than this matrix, or if we write it out, it is the skew-symmetric matrix of the transformed point, negative, plus, minus, plus, x1 prime, 2 prime, 3 prime. Then we have the unit matrix here, and we have here the transformed point. Again, to be evaluated at x equals x0 and a0. So together we have the following situation. We start with the task, which is what is the uncertainty of x prime as a function of a and x. And we have given a with its mean and the covariance matrix of the corrupting parameters p. And x, it has some mean value and some covariance matrix. We linearize, we know how to do this now. And then we can directly from this equation derive the variance covariance matrix of x prime as this Jacobian multiplied with the covariance matrix of the parameters multiplied with the Jacobian transpose plus the second Jacobian multiplied with the covariance matrix of the given parameters multiplied with the transposed. All these Jacobians, of course, have to be evaluated at approximate values, so, but this is now quite simple. Okay, this seems everything very simple and clear. Now I have to finally make a very important point. It took me a month of finding an error in my program, and it turned out that it is that what I show you now, that was a conceptual error. And you know that finding conceptual errors in software is quite tricky because you, of course, assume that you have made a program error. So we find out that there are two options for the linearization of a similarity or a rotation, a motion. We discuss only the motions here. What we did up to now was the following. We have put the two parameters dr and dt in one vector ds and took the motion, approximate motion, multiplied with the small motion and got the motion after this correction. Now, if you write this out, we obtain the following. Here we have the approximate motion with the approximate rotation, the approximate translation. And here we have the small rotation and the small translation. Multiplying out, we get the rotation, the approximate rotation, multiplied from the left with the small rotation. And here we get r of dr multiplied with t, this is this part, plus dt. So we don't obtain t plus dt, which we would expect, but the rotated point, t0, rotated with the small rotation depending on dr. So some people might not like it and just say, I do it differently. So we have an alternative. So let's try the following. We take the approximate rotation and the approximate translation here in this motion matrix. We correct the rotation multiplicatively from the left with a small rotation and the translation additive with a small translation. Because this is a different representation, we need to have other parameters in principle. So I call them d zeta, which is the rotation parameters d rho, and the translation differential d tau. So this looks much nicer. But of course it's different from that what we did before. So we have two alternatives and we would like to know what is the difference really. Now, let's assume we have the same approximate value or the same mean value, and the changed motion should be the same. That means we have the same type of distortion. Then these two matrices should be the same. Okay. Now we immediately see that in order that these two expressions are the same, the d rho and the dr should be the same. So the two representations which we discussed don't distinguish by their rotation parameters. That's fine. Now let's have a look at the translation. So the translation component in the first representation was this with the rotated, differentially rotated translation vector, which may be large, plus the change in the translation. And in the second representation, we just had the additive correction. Now, let's assume that these two are the same. That means these and these expressions are the same. Then we can derive d tau by subtracting t0 from this expression. So we get r of dr multiplied with t0 minus t0. So we get here r of the small rotation component minus the unit matrix multiplied with t0 plus dt. Now, what do we see here? A small rotation is a unit matrix plus a skew-symmetric matrix up to first order. And that means if we subtract the unit matrix here and here, we are left with the skew-symmetric matrix of the rotation vector multiplied with t0 plus dt. Now, this is not an expression which we like because we would like to have the dr on the other side. So we exchange these two values. Dr cross t0 is the same as minus t0 cross dr. So we finally come up with d tau is dt minus the skew-symmetric matrix of the approximate value for the translation multiplied with the small differential rotation vector. So this is this expression. And because dr and d rho are the same, we get a similar expression in the other way around. So obviously, the change in the translation not only depends on the change dt or d tau, but also on the rotation, on the translation part and the small differential rotation. So they are linked together. We can put this into a compact form. So we have linearized relations between the two parameter vectors. So we have here ds, which is dr dt, is the same as d rho d tau multiplied with this matrix. And that's the other way around. So if we now have a covariance matrix for theta and do variance propagation, we come to a covariance matrix of ds, which is not the same, because we have not a unit matrix here, but we have a off-diagonal term S of t. The interesting thing is, if you do the estimation, the parameters for the estimated motions are the same, but depending on whether you do the one or the other linearization, you come out with two different covariance matrices. That means, in general, though the estimated motions are the same, their parameters, their covariance matrix, turns out to be different. So the covariance matrix of the parameters S and those of the parameters zeta are not the same. What is clear because we see here a unit matrix here, the rotation part, the two rotation parts, that means the corresponding 3 by 3 submatrices of the covariance matrix, are the same. But the translations parts are not the same. And also the covariance between the rotation and the translation are not the same. So this you should take care if you do programming and compare results from your estimation and from the estimation of somebody else. If you don't use the same update rule, the same type of linearization, you will come up with two different covariance matrices. And don't be astonished, this should be so. Okay. We discussed the linearization of a similarity. Of course, this is very useful for variance propagation, as we have seen. It can be used not only for single, but also for many points. It can be used for single or concatenated transformations. This will be, we will see in the next lecture. These are kinematic chains, so you have motions or similarities which are concatenated. And of course, if you want to estimate parameters from many points, pairs, which we discuss in one of the following lectures. And we have to take into account that the type of differentiation, how we linearize our similarity or motion, makes a difference in the corresponding covariance matrices. Thank you very much for this part. And the next lecture is on modeling robot arms, which consists of different links like our arm, and they are related by some relative motions. And these relative motions are usually parameterized by what is called the Dynawit-Hartenberg parameters. We will have a look at this, and this is an application for concatenating uncertain motions. Thank you very much. Until next time.